Greetings, welcome. So in this video we're going to return to the Thane Heins bitoroidal transformer. And this is the circuit that I was using previously for that. And what you do is you make a connection to the positive to here, and you make a connection to the negative to there, and you shut those two switches off. Then you take this cap, discharge it across this, and the primary on your bitoroidal transformer, and since it's bitoroidal you have two secondaries, and you gather what comes off of the secondaries through two full wave bridge rectifiers. Now when I did this, one of the things that was interesting was looking at different timings in relation to the resonant frequency of the LC tank circuit between the primary of your bitoroidal and your cap. And there's very different behavior depending on the timing. So in some ways it behaves a lot like the buck boost, and that's a good part of the reason why I spent a good half hour really doing a deep dive on the buck boost and trying to figure out why it transforms voltage real well in some places and doesn't transform voltage at all in other places. And I finally figured that out. So if you want to know, then you got to watch the last video to the end. So as with the buck boost, with the bitoroidal, if you take this cap and discharge it to 0, and then that's when this cap is at 0, that's when you make and break the connection. It transforms voltage like a champ. However, the cap has gone from the starting voltage down to 0. What I was doing a few videos back, a long time back, like a couple months ago now, was I would let the cap go from 10 to 0 to -8, back 0 to 7, and shut everything down there. And there are a couple things that happen then. The first is that it doesn't transform voltage well. Now, it does transform voltage. If it were a buck boost, it wouldn't transform voltage at all there. You'd never get past your starting voltage. It does transform voltage, just, not real well. On the other hand, you've started off at 10 volts, and you've ended up back at 7 volts, so you just throw in another 3, and you're back to your starting voltage. So in one of the videos in this series, I think it was the one that got the least views, running the bitoroidal transformer, we noted that, if you crunch all the numbers in a spreadsheet, and you have, say, like 1,000 ohm load across your secondaries, that the COP is coefficient of performance is like 1.2 or 1.3 when you're at 20 or 30 volts, which is to me pretty interesting. Thane Heins is right. And then after I'd gathered all the data, I went back looked at it on the spreadsheet, and let's do a pretend game or a thought experiment here. Instead of taking the cap, discharging at 0, -0, back to positive, so you go from like 10 to 3, what if you cut things off when it goes from 10 to -8 instead of +7? Now there's a couple things. Because you have the full wave bridge rectifier, when it goes back up, you're going to get more out here. But at the same time, instead of going from 10 to 7, you're going from 10 to -8. So let's pretend these are non-polarizable caps, or polarizable, I'm sorry. Let's pretend you just switch the cap over. So now you've gone from 10 to 8 volts, and you only need to put 2 back in instead of 3. Or something, that trend. I'm not sure that those exact figures are right. And so looking at it on the spreadsheet, I thought, I wonder if this would be a little bit better. Maybe if you cut it off there, the COP would be like 1.4 or something. Well, it wasn't. If you cut it off there, the COP, when you looking at it on the spreadsheet, is like 2 or 3 or 3.5. When you're at at 20 or 30 volts. Huge improvement. And that's because, Thane talks of this as a magnetic diode. I don't even have dissimilar materials. I'm just doing it with like all ferrite cores and air gaps and things like that. And so that's why it's a really big improvement if you do it there. But let's just tear it apart and get it so this cap will charge one way, discharge, and then charge the opposite way. And then we'll put the rest of it together. So let me stop yammering and actually just tear this apart. I'll leave the bridge rectifiers in, and I think I can fit it all on this same little mini breadboard and see what we get. So here's just the very first part. And what we have pin 13 goes high for a second, and then it goes low for a second, and then pin 12 goes high for a second, and then low for a second. So pin 13 comes out to here, and it triggers both of these solid state relays. So they turn on, then they shut off, and then these two turn on, and then they shut off. So how we have it set up right now, if we put a cap between here and here, then all that's going to happen right now is this cap will charge up, and then it will sit there. So we have the power at 2 volts, and we see that charges up to 2 volts, and then it's just slowly leaking out through the meter. So now what we want to do is charge it the opposite way. So what we're going to do is we're going to take the positive now and connect it right to where it was negative before. I know you might be thinking, you're crazy, man, it's going to be a short. And then we're going to take the negative here and connect it to the positive. And the nice thing is that these are all opto-isolated alternating current solid state relays. So if all goes well, when we put the cap in, we'll see it charge up to 2 volts first one way and then -2. So a lot easier to do nowadays with these opto-isolated relays than back when Bedini and Cole were doing it, where there were just, this would have taken a lot of transistors. It would have been a lot more complicated. And it didn't work. And there was a dead short. So that's one reason why you don't want to do this at like 20 volts when you're putting it together. And what it was I'd copied this code from before, and I had pin 8 low. So in other words, pin 12 was always high. But everything else was correct, so now it should work. Okay, so now we're good to go. So we see it goes from 1.9, then charges the other way to -1.9, and nothing's shorting out or anything like that. So beautiful. Now there's one more wrinkle that we have to add in, and we get to find out whether it's going to be a complicated ordeal or a simple thing, because I don't know yet. When it gets to 1.9, then we want to discharge it through here. And then that's when, if it's going through a coil, it's going to be springing back negative. Then charge it up, and maybe you can even discharge it through the same one. I don't know if you'll need another switch. That's what I'm saying. Who knows what? We get to see what happens. So now what we do is, after this is charged up, then we throw pin 9 high for a second, and then pin 9 low. I need a delay there. So pin 9 high for a second, then pin 9 low, and then pin 12 high. So this should then charge the cap up, and then you put a line between the positive out to this other switch, pin, which is controlled by pin 9. That makes a connection between there to the negative leg, and it discharges. Now we're not quite there, but we're almost there, so let's see what this does. Okay, so it charges up to 2, and then discharges to 0, and then it charges to -2. Yeah, it's doing what we want. I just left it discharged for 3 seconds. So what do we see here? That's it, discharged for the 3 seconds. -2, positive 2. So there, and then it flipped. You see that went from -9 to 1.9. I don't know if I did a good job explaining that. So what it's doing, it's charging up to 2 volts, and then it's shorting across this line. This will be your coil. And then it's charging up to negative, but then it's not shorting, then it's just charging up to negative and then charging up to positive again. So now we want to do the same thing on the negative part. Charge it up to negative, discharge it, and then charge it positive. Now, unless I miss my guess, we don't have to do anything except for add some code to send it through here again, because everything's opto-isolated, and these are all alternating current solid-state relays. So I think all I have to do is take pin 9 high, pin 9 low, and put it in a second time there. So I just put that same code, pin 9 high, pin 9 low, after it charged up negative, and it's gone through the same switch. So this is where it could all go sideways, but it looks to me like it would work. Let's find out. Okay, this is beautiful, if you don't mind my saying. So it charges up to 2 and discharges. I'm just leaving it there a long time because last time now it charges up to -2 and it discharges. So now what we'll do, and the video is getting a little bit long, but what we'll do to wrap this video up is, instead of this white line, we'll use the primary of a bitoroidal transformer, and we'll set the timing for where this thing swings most negative, and then you can see why I'm setting it up this way. But we're not going to do anything yet with the secondaries. That'll be the next video, is we'll see really how this thing is behaving and gather data on it, and then, as I said, maybe test it with some batteries. There's nothing to show there. I mean, it'd just be like, look, it really is going to, this voltage. I mean, how would you know? The important stuff is just showing the build of the circuits and the reasoning. So that's how you build it, and it's doing what we want. So now let's just make it swing. So I've got like a few of these things lying around with like different area apps and all that, and that's going to be, we'll be looking at that stuff too. But the next part here is to replace that white line with the primary that we're going to be pulsing. And if we want to make the thing swing the way we want it to, then we want to know where the cap would go most negative. So we want to know the induction of the primary. So I'm seeing about 2.72 millihenries off of this primary coil. And so if we go into our spreadsheet and we change this, then it calculates everything for us. And we see that right around 518 microseconds is where the cap should swing most negative. Now it might be, a couple or a few percent off just because of the measurement error, and because maybe this isn't really a 10 UF, I should measure that too, but it'll be close enough to see that it works. So we go back to our code and we set the on time, the discharge time, to 518. Okay, so I replaced the white line that it was discharging across with this, so it's now discharging across the primary, the bitoroidal, and set the timing as we saw from the spreadsheet. So when we turn it on, what do we see happen? See it charge to 10 volts, and then it goes to -8.9, then -10 to it's almost going to 9, -8.9, -10, back to just about 9. So this works. Now, granted, it's unloaded right now, but you're getting 90% of the way back to where you started. Whereas if you let it swing back positive, you might get 80% of the way back to where you started. So that's why this is really nice. And you don't lose very much across the secondaries, in large part because this isn't a very good bitoroidal. I mean, it's all the same material and everything else, but that's what you want. You know, it's as the song goes, it don't mean a thing if it ain't got that swing. So that's how you do it. And in next video we'll see how well it does. And I'm actually, I'm curious about this stuff now, so that video should get out fairly quickly. So thanks for coming along. Stay healthy. Ciao for now. Bye.